So I'd like to talk about a topic that's in science fiction. This is something that's just for fun. I think to play on the PH in physics, the word fun. But it's artificial gravity, right? If you've ever watched a science fiction movie or show where people are in this the structure in space where they're walking around. Like there's gravity, right? They're not floating around. Things are resting on the floor. They're walking on the floor. Things fall. Is that possible? Can we create artificial gravity? And the answer is yes. And you probably see how it needs to be. It can be done. Is this structure has to be rotated. So let's say that the structure is like a cylinder, and people, they live on the inside of this cylinder, and it rotates about this axis. I'm going to say it rotates this direction. And so this cylinder has a radius r, and what happens is if there's friction between these people's feet and the surface. So as the surface rotates, friction, they want to stay put, but if they would stay put, they would slide on the surface this way relative to the surface. So friction, there's a force through static friction that way. So that accelerates them along the tangential path, and so that's what keeps them just from sliding. But what keeps but that friction will accelerate them this way, so they develop a velocity this way, and they'd want to keep on traveling that way, but they don't. They travel in a circle. And in order for them to travel in a circle, as this rotates, there needs to be a centripetal acceleration, therefore a centripetal force. And that force is the normal force. The normal force acts as the centripetal force. Now, if you remember in our lecture about gravity, our perception of weight is derived from feeling the surface exert the force on us. And so that's the normal force. That's why if you were in an elevator and you cut the cord and you begin to free fall, you feel weightless because you and the elevator are accelerating downward at the same rate. The elevator exerts no normal force on you. And so it's us feeling surfaces exert normal force on us that gives us our perception of gravity and weight. And so the normal force, if we can rotate this cylinder that has a radius r at a speed v, so that the people move at a speed v, we can find it so that the required centripetal force, the normal force, is equal to their weight on Earth. And so their weight on Earth, their weight on Earth is mg, where g is the field strength, gravitational field strength at the surface of the Earth, or the acceleration of gravity. And so we want the normal force to equal mg. And we know the normal force is going to equal the person's mass times their centripetal acceleration, because that's what's accelerating them in this circular path. And centripetal acceleration is v squared over r. So now we have mg equals mv squared over r. So it doesn't matter what the mass of the person is. So g equals v squared over r. So if the cylinder has a given radius of r, g times r equals v squared. And so we get the square root of gr equals v. Alright, so that's this velocity that the rim of the cylinder needs to have in order to simulate gravity. It's the square root of the acceleration due to gravity times whatever the radius of that cylinder is. But what might be easier to program in is like, well, what is the rotational period? How long does it take to make one rotation? And so V is 2 pi r over that rotational period, t being the period, how long it takes to make one rotation. We plug that into here. Square root of gr is 2 pi r t. Solving for t, we get 1 over the square root of gr equals t over 2 pi r. And we multiply that over there. I'm going to come over here. T equals 2 pi r, the square root of g times r. Now this is r to the 1/2, to r divided by r to the 1/2. And so remember, when you divide numbers, you subtract the exponents. This is the same as r to the 1 minus 1/2, which is r to the 1/2. And so this can be rewritten as 2 pi, and r to the 1/2 is the same thing as the square root of r, times the square root of r over g. So this should, in theory, have units of seconds, right? 2 pi is unitless, r is meters, g is meters per second squared, square root. We get 1 over 1 over second squared. Sure enough, that is units of seconds. Yep. So that's the orbital period. So that's how many seconds. So if we're going to create an installation in space where people can walk around on the inside and feel like they have the same weight as they have here on Earth, and if that installation has a radius of r, we'd have to set it up so that the time it takes to make one revolution is equal to 2 pi times the square root of that radius divided by the acceleration due to gravity on Earth, 9.8 meters per second squared. And so you have to put like little thrusters that speed it up to that speed, and so that it has that orbital period, and then maintain it. If it starts to slow down, you got to speed it up again. If it speeds up, you got to slow it down. But maintain this orbital period, or this velocity at the rim, and because if it spins faster, the normal force, the centripetal force will be larger. So if you have a larger normal force, you'll feel heavier than you do on Earth. If it spins, so if t is any smaller than this, it means it's spinning faster. You'll feel heavier than Earth. If it spins slower, right, then it doesn't require as large of a normal force. So if t is any larger than this value, then you'll actually feel lighter than you do on Earth. Right? So, so to have that exact same sense that you do have on Earth of gravity for a given radius r, you have to dial it in so it has this rotational period, this amount of time to make one rotation, and so the outer rim is traveling at whatever this speed is. So if we ever get there one day, where we're making these installations in space in which people can live, yeah, we can simulate gravity, right? And if we have like multiple levels, those are different r's, and so they'd have to rotate at different speeds. And so they couldn't move in lockstep, because then they would have different sense of gravity at the different levels. And so different levels would have to rotate at different speeds. And that would make it difficult to get from one level to the other, right? Because they're moving at different speeds. So it'd be easier just to make one shell or one cylinder or whatever. It couldn't be a sphere, because then it has to rotate along one axis, and it won't have the same effect on parts of the sphere that aren't along the equator of the sphere that's in the plane perpendicular to the rotational axis. So it had to be a cylinder. But within that cylinder, you could move around and feel acceleration to gravity. Right? In theory, you could throw a ball things would drop like they would on Earth. You could definitely throw a ball along the rotational axis this way. Like if you throw it that way, that would behave just like on Earth. Right? If you're playing into this axis. If you're playing catch this way, I have to think about that a little more. It's an interesting thought, or whether that ball would behave the same way it does on Earth. I think it might, but I'm not exactly sure. But it definitely would if you're playing along this direction. But so this is just an example of fun. I mean, obviously this is like the thing of science fiction, but it's an application of physics to of something that's just fun and useful.